All right, ladies and gentlemen, as promised, here's a video that addresses the following numbers from the summer math packet. Just want to give you an idea as to how you should go about doing these types of problems, specifically 2, 4, 5, 7, 9, 13, 14, 15, 37, and I'll do a little emphasis on notation for domain and range throughout. So you can kind of fast forward if you want to the pages that you need to see. Otherwise, sit back and enjoy. All right, so here's the first one we're going to look at, 2m. This is one that gave a lot of people some problems, and the first thing we want to do is rewrite this in a way that makes it workable. So I'm going to take those negative exponents and move them to the denominator. So I'm going to rewrite this as x over 1 minus 2x to the positive 3 halves plus 1 over 1 minus 2x to the positive 1 half. And you'll realize that the term in the denominator is not much different from one to the other. The right-hand fraction varies by a full degree. So if I multiply the right-hand fraction by a 1 minus 2x over 1 minus 2x, that will give it a common denominator of 1 minus 2x to the 3 halves. Because remember, this is a to the first, and 1 plus a half is 1 1/2 or 3 halves. So this would be x over 1 minus 2x to the 3 halves plus 1 minus 2x, 1 minus 2x over 1 minus 2x quantity to the 3 halves. And now that I have a common denominator of 1 minus 2x, I can combine the numerators. I have a positive x and a minus 2x, so that's going to be a 1 minus x all over 1 minus 2x to the 3 halves. And that would be a great place to stop. I'm sure that you can make the denominator a full degree by multiplying through by a 1 minus 2x over 1 minus 2x and getting it to be a 1 minus 2x squared in the denominator, but that's about as simple as it needs to be, a single fraction with no negative exponents. All right, this next question, 4e, was one that many of you had a brain fart on, and you knew pretty much how to go about doing the problem, and then your brain stopped working 3/4 of the way through. So assuming that you recognize that this is a factorable trinomial that factors to x times x minus 4 times x minus 2. Most of you got here and then didn't know what to do with this, and you came up with some really weird answers because you were supposed to graph this. Now, we know that the equality piece, that when x is equal to 0, x is equal to 2, or x is equal to 4, this will produce the equals 0 part of the inequality. We have to worry about the less than part. And my suggestion to you would be using these three values, 0, 2, and 4, to set up some regions and see what happens. And when I say regions, I mean there are numbers that are less than 0, numbers between 0 and 2, numbers between 2 and 4, and numbers greater than 4. So let's take a look at what happens if you're between negative infinity and 0, what happens when you're between 0 and 2, what happens when you're between 2 and 4, and what happens when you're between 4 and infinity. Again, we know the equals 2 part is going to be 0, so those are included, but what part of these intervals are included? And I would say just go ahead and choose a number in each interval. So maybe if I choose -1, +1, 3, and 5. And let's evaluate the function at those values and see what happens. So if we evaluate it at -1, we would have -1 times -1 minus 4 times -1 minus 2. And let's see what that gives us. That would be -1 times -5 times -3. -5 times -3 is positive 15 times -1 is -15. And the question is that value less than 0? Well, -15 is less than 0. So then I know that I can take values for x less than 0 and include them in the solution set. Okay, I'm going to do that for each of the values that I chose. So for 1, I would have 1 times 1 minus 4 times 1 minus 2. That would be 1 times -3 times -1. That comes out to a positive 3. and positive 3 is not less than 0. So I know that the interval 0 to 2 is out of my solution set. If I check for x equals 3, I'm going to have 3 times negative 1 times 1, which is a negative 3. Negative 3 is less than 0, so I know that x can take on values between 2 and 4. And then finally, when I try for 5, I'll plug a 5 in, and I get 5 times 1 times 3, which is 15. And again, 15 is not less than 0. That one's out. So when I put it all together, I guess I'll do it down here, I know that x can be less than or equal to 0, and I also know that x can be greater than or equal to 2, less than or equal to 4. And that would be my solution set that you can then transport onto the graph that you needed to do. All right? So use intervals, choose numbers, see how they work. That'll lead you to your answer. I think these particular problems, I want to look specifically at I and L. The J and K weren't bad. Might have just been notation. So just a reminder that these capital letters, the T and the S, indicate the principal value for the inverse tangent and inverse sine function, which means that they have limited domains that you can work on. For the principal values of inverse tangent, you're only allowed to report answers falling between negative pi over 2 and pi over 2. So essentially this asks, when you apply inverse tangent to 1, what is the answer that is between negative pi over 2 and pi over 2 for an angle that has a tangent of 1, and that answer is pi over 4. I saw a lot of people trying to give all values, so pi over 4 plus k pi over 2 type of answers, and in this case the principal value guarantees me only one value. For inverse sine reports values on a different domain. It is negative pi over 2 to pi over 2. So the answer to this question is going to be simply a value between negative pi over 2 and pi over 2. Assuming that we all know that the sine of 7 pi over 6 is negative 1/2, I'm looking for inverse sine of negative 1/2. So where between negative pi over 2 and pi over 2 does sine equal negative 1/2? That is with a reference angle of pi over 6, but it has to be negative, so negative pi over 6 would be your answer. Again, not all values on the real number line, but just those values between negative pi over 2 and pi over 2. So I think that was more just either you didn't pick up on the capital or you forgot about the principal value, or maybe you came from a class where they really didn't emphasize principal value. Many of the problems I saw in this section were just about extraneous answers, so that's probably what we're going to talk about most here. The first one being 7C. As we've talked about with the multiple choice for limits, when we were doing the natural log stuff, there are some things that you should look for when doing logs, and that is sums and differences. They turn into products and quotients. So I would right off the bat rewrite this as log of x times x minus 3 and set that equal to 1, and then maybe even expand that to say the log of x squared minus 3x equals 1. Now to undo the log, we do this thing called exponentiating. So since this is a base 10 log, the common log, if I exponentiate each side using a base of 10, I will undo the log because they're inverses of each other. So that means that x squared minus 3x would equal 10 to the first, or 10. And then x squared minus 3x minus 10 equals 0. X minus 5, x plus 2 equals 0. X would equal 5, or x could equal negative 2. Now, whenever we do things with exponentiation, squaring, stuff like that, we always have to be careful that we didn't generate an extra answer. So if I take both of these values and go back up to the original equation, I have to substitute them in and make sure they both work. Now, log 5 and log 5 minus 3, those are both attainable values that probably do add to 1. However, the log of negative 2 and the log of negative 5 are non-existent. Okay, if you consider what a log graph looks like, you can't go past a number very close to 0. So for this reason, we call x equaling negative 2 an extraneous solution and only report the value of 5. This is by far my least favorite problem on the entire math packet. It's just a lot of work to get this. The idea is to isolate square and then solve for x. So the first thing I want to do is bring this x minus 4 to the other side. So say negative 5, x minus 4 to the 1/2, 6 minus the quantity, x minus 4. And then if I want to get rid of the negative, just to make my life easier, 5 times x minus 4 to the 1/2 is equal to x minus 4 plus a negative 6. So this is 5 times x minus 4 to the 1/2 is equal to x minus 4 minus 6, or x minus 10. Now I want to go ahead and square each side because I want to get rid of the square root. And if you felt really wild, you could bring the 5 over and divide by it, but it really doesn't make a difference at this point. That's going to give me a 25 times x minus 4 equaling x squared minus 20x plus 100. And if I combine like terms, I have an x squared. I have a negative 20x over here, and I'm going to bring over another 25x, so minus 45x. And I have a positive 100, and then the negative 100 from when I distribute here will come over as a positive 100, so plus 200 equals 0. And then factoring this, I get x equals 40 and x equals 5. Because x minus 40 times x minus 5 is the factorization of x squared minus 45x plus 200. Now going back again, whenever you do this squaring piece right here, there's the possibility that you generated an extraneous root. So you have to check x equals 40 and you have to check x equals 5. In doing so, you will see that x equals 40 does satisfy the equation, but x equals 5 does not. So you actually get like negative 4 equals 6 when you plug it back in. So the only solution for G is x equals 40. All right, a little trig equation again. Notice the restricted domain here. And while we're here, why not I just talk about some of this notation. So if you're looking for x values that are restricted to be between 0 and 2 pi, another way to write that is that this is a closed interval that includes 0, and then we're going to put a comma to separate that this is where the x is going to be, somewhere between 0 and 2 pi, and it is inclusive. So again, we use brackets for inclusive, we use parentheses for exclusive. So I can only report answers between 0 and 2 pi. And whenever you have a quadratic, you bring everything to the left, set it equal to 0, and see what you get. So this is what I'm going to be dealing with. I must have a 2 sine x and a sine x. I want this to multiply to a negative 1, but add to a negative 1 as well. So I'm going to give the negative 1 over here. So I get a negative 2 sine x when I FOIL, a plus 1 here. So I'm looking for where sine x is equal to negative 1/2, or where sine x is equal to 1, again only on the domain 0 to 2 pi. I think we all know that sine is equal to 1 at pi over 2. And then sine x equals negative 1/2 on 0 to 2 pi. If it's helpful, go ahead and sketch yourself a little sine curve. Throw in the value of negative 1/2. You'll realize that there are two values in which this happens. Again, use your reference angles. The reference angle for negative 1/2 is pi over 6. So one of them occurs just after pi. That's going to be 7 pi over 6. And one of them occurs just before 2 pi, or 12 pi over 2, which would be 11 pi over 6. So we get three values for solutions of this: pi over 2, 7 pi over 6, and 11 pi over 6. A lot of people missed the pi over 6 pieces, or forgot completely about the pi over 2, or some mixture of both, or you just skipped it. I don't know. Somebody just skipped it. I don't know why. All right.